Conceptual Physics at Delaware Tech, Chapter 19, Vibrations and Waves. In this unit, we'll talk about vibrations of a pendulum and what vibrations actually means. We'll talk about how vibrations relate to waves and talk a little bit about the description of a wave. We'll talk about wave speed and how it relates to some of the characteristics of a wave. We'll talk about the two major categories of waves, transverse waves and longitudinal waves. And we'll talk about wave interference, standing waves, and Doppler effect. And then finally, we'll end with bow waves and shock waves. So, vibrations. Vibration is essentially a wiggle in time of something. It could be a macroscopic object like a pendulum swinging back. Going back and forth would be one vibration. It could be a particle vibrating in space. So an up and down motion would be considered a single vibration, whereas a vibration that moves in both space and time is called a wave. Now, what do I mean by that? Well, let's assume my finger is a particle vibrating or something vibrating, and I'll make it up and down so it's obvious, okay? And I'll do it slowly so it's very obvious. So that would be a vibration. It's vibrating, it's a periodic wiggle in time. It's moving back and forth in time. But if I move it in space as well, it becomes a wave. Now, what do I mean by that? Watch my hand. I will just move it across, and you see, if you trace my finger, you see it forms a wave. All I'm doing is moving my hand at a constant speed across, and now that wiggle becomes a wave. And so a wave extends both in time and space. It's moving up and down in time, and it's moving across in space. So it extends from one place to another. It's the wave that's moving. So examples of waves, the two major categories the two major examples we'll talk about quite a bit, but though we'll talk about a third kind, are light waves. Light waves meaning any wave in the electromagnetic spectrum. So this could be radio waves, microwaves, infrared waves, visible light waves of the colors that we see, ultraviolet waves, gamma rays, and X-rays. Okay, but the other category is sound waves. Now there are a number of big differences between these types of waves. Light waves, the EM spectrum waves, they don't need a medium. And in other words, they can go through a vacuum of space. They can go through matter too, that allows them to. I mean, you can have visible light going through glass, for instance, but light waves, electromagnetic waves, do not need any matter to propagate through. They can go through the emptiness of space perfectly fine. In fact, they go through empty space better, faster than they do when they go through matter. Sound waves, however, it's the opposite. Sound waves absolutely require matter to go through, like a solid, a liquid, a gas, or even a plasma. They absolutely require a wave. They actually require the wave to go through matter, and that's because matter is involved in forming the wave. All right. So a vibration is a wiggle in time, boom, 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 boom. And a wave is a wiggle in space and time. It's moving. All right. Simple as that. So movement of a pendulum. So now we're just moving really in time. We're just going back and forth, back and forth. We're not really moving the pendulum across. And if we swing a simple pendulum, this could be a stone on the end of a string, or if you have a real pendulum or a grandfather clock that's freely swinging, you can watch it. And the end of the pendulum, what we call the bob of the pendulum, will actually swing down with an acceleration. It will actually get faster, then get slower and come to a stop, get faster at the bottom, and then get slower and come to a stop. And this could be modeled as if it was just the bob rolling down an incline, so that it was a little bit slower acceleration than the acceleration due to gravity. But it can do that back and forth. And so this pendulum, because it's coming down and then going back up, and it's going down with the length of the pendulum and then coming back with the length of the pendulum, the time it takes to swing, the frequency it takes to swing, and the time it takes to swing is dependent on the length of the pendulum. The longer the pendulum, the longer it will take to go back and forth. That's one cycle. Back and forth, one cycle. Longer the string, the longer the pendulum, the longer the cycle. However, it has nothing to do with the mass that's on the end of that string. That string could have whatever mass, as long as the string is taut, or it's a stick that's swinging. It only is dependent on the length of the stick and not the mass of the end, the ball or the stick or whatever it is that's swinging. It's independent of the mass. It is dependent on one other thing, and that's the acceleration due to gravity, but we're not going to be doing pendulums on any other planets, so we'll just consider it dependent on the length. So the longer the length, the longer the period. If you have a short pendulum, it'll go back and forth on its own pretty fast. If you have a long pendulum, it's going to take longer to swing back and forth. All right, a 1 meter long pendulum has a bob, that's the weight at the end, with a mass of 1 kilogram. Suppose the bob is now replaced with a different bob of mass 2 kilogram. How will the pendulum's period change? The period is the amount of time it takes to go from one end and then back, all the way back to the original position. Will it double? Will it half? Will it stay the same? There's not enough information. Well, I just finished letting you know that it is independent of the mass. It has nothing to do with the mass. It's only dependent on that 1 meter long length. So it will remain exactly the same. It depends on the length, not on the mass. The mass has no effect, just as the mass has no effect on the acceleration rate. If you drop a ball, the speed that it has at any one time as it speeds up as it's moving will happen no matter what the mass of that object is, as long as we ignore air resistance. A 1 meter long pendulum has a bob with a mass of 1 kilogram. Same pendulum we're starting with before. Suppose the bob is now tied to a different string so that the length of the pendulum is now 2 meters. How will the period of the pendulum change? It will increase, it will decrease, remain the same, not enough information. Well, remember, the length of the pendulum will change the length of the period. It will take longer, so it will increase. So the pendulum's period definitely depends on the length of the pendulum. Specifically, the period of the pendulum increases with increasing length. So the amount of time to go forward and back to the original position will increase. Now you'll notice I never said proportional. They are not proportional. It's more complicated than that, so we're not going to go into it. There's a formula that involves a square root, so it's not a direct simple proportion, but if one goes up, the other goes up. If one goes down, the other goes down, just not by the exact same factor. So wave description. So when we're looking at these waves have a very definite shape, this curvy shape. And we call that curvy shape a sine curve based on the mathematical sine curve that you might have learned if you ever took trigonometry. It's also referred to as a sinusoidal curve. Sinusoidal curve just means related to the sine curve. So let's back that up a little bit. So the sine curve is obtained. You can do this in this particular picture. What they did was they took a pendulum that was filled with sand and it had a little hole in the bottom of it, and it would swing back and forth, and it was just moving in time, not really going anywhere except back and forth. And then the paper underneath of it was moving in space underneath, so that you could see the path as it changed with time. So what this represented, this curve represents, is that now the wave is down here, then it's up, then it's up, then it's up to the top, and then it comes down gradually, it comes down, and it just repeats. So it's moving with time along that curve, and the sand will trace out that pattern on the sheet. You could just do this with your finger, going up and down, and then move your hand, and you can look at the tip of your finger, and you'll see the same exact curve. So we describe waves with a number of different characteristics. There are several characteristics that you should be aware of whenever you're looking at a sine type wave, a sinusoidal wave or sine wave. And so if we imagine a different wave here, this is a wave where it's generated by having a bob, a weight hanging on the end of a spring. And the spring is just pulled down, so now it's springing back and forth. So gravity pulls it down, and then the spring force pulls it back up, and gravity pulls it down, and it's just going up and down at a changing rate. And then the paper is moving underneath it, and it traces out this pattern, and you get a wave. That's one way to make the wave. So there are a number of characteristics we have to look at. One is called the crest. The crest is just the highest point in a wave, and these will repeat. You'll find a crest, and then another crest, and another crest, and it'll keep on going for the length of the wave, and you'll get one crest for every repeating wave. It's a repeating part of the waveform. It's the highest point. The lowest point of any wave is called the trough. So the troughs are the bottom of the curves. The crests are the top of the curves. Now the amplitude, you might think, oh, that's the distance between the top and the bottom. No, it's actually the distance between the top, a crest, and the middle of the curve, or it's the it's the distance between the bottom, the trough, and the middle of the curve. In other words, it's half the width of the whole wave. That's the amplitude. So when we say amplitude, that's what we're talking about. Frequently, people will be thinking of the whole width, but we're really talking about half of that whole width. So it's the midpoint to a crest or the midpoint to a trough. The wavelength is the length of a single repeating unit of the wave. Remember, you can say starts up here, it's going to come down and come back up, and that's a whole wave. So crest to crest, crest to adjacent crest, that would be the length, that measure of length, and it would be, say, in meters or centimeters, whatever unit of length you're using. It's an actual length. That's the length of the wave. And some waves have incredibly tiny wavelengths, like gamma rays have wavelengths that are smaller than an atom. But you have other wavelengths like radio waves that are bigger, that can be as wide as a mountain if you really want a wide radio wave. Some of them are. So the wavelengths can be pretty much any number you can imagine. And that would be measured from crest to crest, or from trough to trough, or any point. If you look at this graph, you'll see there's a point here where it says wavelength. It points from some random point on the curve and then follows it around until it comes to the repeating point at the end of that curve. Notice there's another point along the way that has the same Y position on the curve, but that's not the same point. It has to come back up to be just like the original point. But any identical points in the curve, that distance between them, that's the wavelength. But it's easier to measure between adjacent crests or adjacent troughs. We have another term that goes hand in hand with the wavelength, and this term is called the frequency. So frequency is how frequent a vibration occurs, and the way we measure this is how many times does a wave go past a certain point per second. How many waves how many waves go past it in 1 second per second. So the unit is per second, second to the -1 or 1/2. And this was named after Heinrich Hertz, so we call them hertz. And you probably heard when people are talking about frequency of a radio station, megahertz or kilohertz, you may have heard with the speed of computers or cell phones in the gigahertz, that would be millions of hertz, billions of hertz with gigahertz. So there could be very, very high frequencies in some cases for certain waves. Or you can have very low frequencies where it's only one wave per second. That would be 1 hertz, 1 cycle per second, 1 vibration per second, one whatever it's doing per second, that's a hertz. So mechanical objects, things swinging like a pendulum, that would have a very low level of hertz. You might have 1 hertz. It would take 1 second to go across and back. So it has to go back and forth for 1 cycle to be complete. And if it was one of those that happened in a second, that would be 1 hertz. If it went twice like that, it would be 2 hertz, 2 cycles per second, 2 total vibrations per second, 2 waves per second, whatever, however you want to call it. Okay, so sound, for instance, sound that we can hear, that humans can hear, especially when they're younger, the range of sound we can hear is anywhere from 20 hertz, that means 20 vibrations per second, or 20 whole waves of sound passing a certain point in a second. Those are very, very deep sounds that only very big animals tend to make, like elephants or blue whales out in the ocean. Okay, to all the way up to extremely high frequencies like 20,000 hertz frequencies. These are the super high pitches that you can just barely hear before you stop hearing them, when only dogs can hear them and other animals. That's the frequency range for human. And this is narrowed as we get older. We will hear the high end will come down dramatically as you get older. I have severe hearing damage, so my hearing is compromised above 2,000 hertz. So if you hear me talking loud, I'm not yelling. I've forgotten that I'm missing my hearing, so I have to bring my voice down, which is what I'm doing right now. But I usually will talk louder, and it's not that I'm yelling, it's just I can't. Okay, so radio waves, now when I say radio waves, I don't mean sound waves that might come from a radio or a source of radio. I mean the waves that a radio station puts out that eventually reach you. These are electromagnetic waves. These are part of the light electromagnetic spectrum. So these move the speed of light, okay? And radio waves tend to have frequencies in the hundreds of millions of hertz. In other words, they do that vibration of their wave 100 million times in a second. Now, this sounds like a gargantuan number. In fact, if you look on your FM dial of a radio, if you have it in the car, and you'll see the top numbers typically 107, 108. This refers to 108 megahertz, 108 million hertz. That's 108 million vibrations in a second. And that sounds like a really large number. But for light, for electromagnetic waves, this is actually some of the lowest numbers. They get much, much more, much higher frequency than this for electromagnetic waves. Cell phones have an even higher frequency. They tend to be in the gigahertz. That's billions of hertz. Giga means billion. So cell phones, and sometimes you'll see this in computer chips that are processing in the gigahertz range. All right. So frequency is how many to and fro vibrations, how many cycles, how many wiggles happen per certain time. And usually that time is per second. So it's the number of waves per second, the number of vibrations per second, the number of wiggles per second, the number of cycles per second. However you want to say it. It's the number of whole waveforms in a second. That is the frequency. And you would calculate that by dividing the number of waves or cycles or frequencies or swings of a pendulum by the number of seconds, and that'll give you the number per second. Seconds on the bottom. We abbreviate in this class frequency with an F, a little f, a lowercase f, but in most more advanced textbooks, you'll see it abbreviated with the Greek letter nu. The Greeks will call it ni. It looks like a curvy V. That is the Greek letter for our letter N. But that we won't be using that in this course, but in case you do look at some other sources, you'll see that means the same thing. So an example, if you have 20 vibrations of whatever, 20 cycles, 20 vibrations, 20 waves passing past a certain point in 1 second, that's a frequency of 20 vibrations per second, or 20 hertz. If you had 600 cycles or 600 vibrations or 600 waves in 10 seconds, you just divide the number of vibrations by the number of seconds. 600 divided by 10 seconds would be 60 per second. Per second is second to the minus 1, or 1 over a second, and those are equivalent to the unit hertz. So it's 60 hertz. So in addition to frequency, we have another way to describe waves which is directly related to frequency. It's the inverse of frequency. It's called the period. It's abbreviated with a capital T because it is a unit of time. Remember, frequency is per time, seconds to the minus 1, or 1 over seconds, or per second. Well, period is just in seconds directly. So while the frequency is how many cycles per second, how many waves per second, the period is how many seconds per wave, how many seconds per cycle, how many seconds per wiggle, or whatever you want to call it. So period is exactly the reciprocal of frequency. Period is 1 over frequency, and frequency is 1 over period. So if you have 1, you just plug it into a calculator and hit that 1 over x button. Some calculators have a button that says x to the minus 1 power. It's the same thing. That's your reciprocal button. You type in period, you hit that button, you'll get frequency. You type in frequency, you hit that button, you'll get period. Very quick. Period is in units of seconds. Frequency is in units of per second, which is the same as hertz. For instance, a pendulum makes 2 vibrations in a second. So it goes back and forth twice in 1 second. That's two full swings back and forth in 1 second. That's a frequency of 2 hertz, 2 per second. The period is 1 divided by that. So it's 1 over 2, 1/2, and seconds, and the unit would be in seconds. 1 over per second is just seconds. So The period in this case would be half a second, 0.5 seconds. So a sound wave has a frequency of 500 hertz. Remember, frequency is it's 500 hertz. 500 waves will happen in 1 second. 500 vibrations in a second. 500 waves will pass by a certain point in a second. 500 wavelengths will happen in 1 second. What is the period of vibration of the air molecules due to the sound wave? Well, air is what's vibrating in a sound wave. It's actually compressing and expanding as the wave is moving through, and we'll talk about that a little later. But if you have a frequency of 500 hertz, what is the period? 1 second, 0.1 seconds, 0.002 seconds, 500 seconds. Well, remember, the period is just 1 divided by the frequency. So it's 0.002 seconds. The period is the reciprocal of the frequency. The frequency is the reciprocal of the period. Because frequency is how many cycles per second, and period is how many seconds per cycle. You just flip them. You flip the number, you flip the unit. So period is 1 over the frequency, 1 over 500 per second is 0.002 seconds. That's the number of seconds it takes one cycle to whip on by or to vibrate. A frequency of a particular wave is 20 hertz. Its period is 1/20th of a second, 20 seconds, more than 20 seconds, none of the above. Well, if the frequency is 20 hertz, that's 20 cycles per second. Well, that's 1 second per 20 cycles. 1 second per 20 cycles is 1/20th of a second. So again, same rules that I just showed you. It's just, you just flip the number, you flip the unit, and you get 0.05 seconds. All right, so let's talk a little bit about wave motion. Don't confuse wave motion with motion of the matter, especially with sound waves or water waves, which are even different from the sound waves and the light waves, the electromagnetic waves. Waves of any kind propagate energy. Something is doing this, something is vibrating over time and moving through space, but it's not the matter that it's going through. So, for instance, sound, the air as sound's going through will compress and expand, but it's not traveling. It might move a little bit to compress and a little bit to expand, but the air over here at the end of the wave will still be over here, and the air over there will still be over there. It's the wave that went through the matter, not the matter moving as well, okay? And so matter might move a little bit from its original position back and forth or up and down, depending on what kind of wave. In a sound wave, it'll kind of compress and expand. In a water wave, it'll actually make a little loop. It'll go down, it'll go up, it'll go down, it'll go up in kind of a little oval shape. But the water over here will stay over here, and the water over there will stay over there, but the wave will travel through the water. It's the wave that's moving, not the matter. It's the energy that's moving, propagating, not the matter. So, for example, if you drop a stone in a quiet pond, the ripples will move. You'll see the ripples move, but the water is not actually moving across the pond. The water in that middle part didn't move out with the waves. The waves travel. When you look at grass in a field, or if you're looking at a wheat field or a cornfield and you see the wind rushing through, you can see the wave moving through the corn or the wheat because the branches will move together and then spread out, move together and spread out, and you'll see this wave moving across. But obviously they're still planted in the ground. They're not going anywhere. But the wave has moved across the field, not the actual plants that the wave is moving through. And the same thing happens with molecules in the air. When you have a disturbance in the air, that's what causes sound. They'll move a little bit, but it's not the molecules that are moving. It's the wave that's moving, and the molecules in the air are helping propagate that disturbance. They're disturbed, they're undisturbed, they're disturbed over here, they're undisturbed. These are disturbed over here, and they will propagate it, but they're not actually moving with that wave. Okay. Now, wave speed is really easy to calculate if you know the frequency and you know the wavelength. You just multiply them together. What is wavelength? It's the length of a single repeating unit of wave. We might measure it in meters. So it's a meter length. We're multiplying it by a frequency. It's how many of these flyby per second. It's how many meters of these per second. When you multiply those together, you get meters per second. So the frequency is in hertz, that's per second, and the wavelength is in meters. Meters times per second is meters per second. That's a speed, and that's how you calculate the speed of a wave. And we can write this as v equals f times lambda. Lambda, the Greek letter lambda, that's the Greek L, it's that funny squiggle. It's just, you can write it as a slash and then a little slash down from it. You don't have to be fancy with it. Frequency times wavelength, f times lambda equals the speed of the wave. And this will be true for any kind of wave, whether it's a sound wave, a water wave, an electromagnetic spectrum wave of all the different kinds of light in the electromagnetic spectrum. It'll always work. Frequency times wavelength equals the speed of that wave. So if I rearrange this formula and solve for f instead of for v, I get frequency is just the speed of the wave, v, divided by the wavelength. Or wavelength is just the speed of the wave divided by frequency. So it's a quick way to solve. If you have any two of these, you can get the third one. And all of these formulas are in your formula sheet. I remember the first one and be able to derive the second two very quickly if I were you, but you have it. So don't worry about all these new formulas. Now, if you look at this first formula, you'll notice that the velocity is on one side, the speed of the wave is on one side, and the frequency is on the other. So frequency is directly proportional, speed is directly proportional to frequency. But speed is also directly proportional to wavelength. They're both in the numerator of that first equation. There's no fraction, so they're both automatically in the numerator. So speed is proportional to frequency if you don't touch wavelength. If wavelength stays the same, if you bump up frequency, speed will change. If you bump up speed, frequency will increase. They both increase the same way. They're both up or they're both down if wavelength is constant. Likewise, on the right equation, of the right proportionality here, if you keep frequency the same, and that happens in all cases of light reflection, sound reflection, and light refraction and sound refraction. Anytime light's traveling or sound's traveling, the frequency will stay the same when it's bouncing off of things or going through things. But the speed will be proportional to the wavelength. So if the wavelength goes up, the speed will go up. If the wavelength goes down, the speed will go down, and vice versa. Okay, directly proportional. But what if you have a situation where the speed is constant? And this happens a lot when we're looking at the speed of light, different types of light in a vacuum. In a vacuum, all forms of light have exactly the same speed, the speed of light. Okay, and we call it, instead of v, we would call it c. So in that case, when the speed of the wave is constant, the wavelength and the frequency are inversely proportional. So if you look at any one of the two equations where it says here f equals v over lambda or lambda equals v over f, you see that one's in the numerator, one's in the denominator. So the wavelength and the frequency are inversely proportional. If the speed is constant, those two will balance each other. One will go up, one will go down. One will go down, one will go up. They are inversely proportional. Okay. So for example, a wave has a wavelength of 0.2 meters. Okay, so the whole wave is about 0.2 meters. 0.2 meters is 2 cigarettes. If you want a tenth of a meter is a cigarette. That's how I remember it. I don't smoke, but that's how I remember it. It's a convenient unit. And then, so 0.2 would be 2 of those. So there's the wavelength. That's a pretty big wavelength for anything, but in water, that's not a big wavelength. Okay, so a wavelength is 0.2 meters, and this happens with a frequency of 2 hertz, 2 per second. In other words, 2 of these fly by every second. What is the speed? Well, the speed is just the wavelength, 0.2 meters, times the frequency, 2 per second, 2 hertz. 2 per second times 0.2 meters is 0.4 meters per second. Don't worry about the units. I'm generally not going to throw you off with complicated changes in units. I'll give you units that will work for you in equations. All right, so a wave with a wavelength of 10 meters, all right, so from crest to crest is 10 meters, one repeating unit, 10 meters, and a time between crests is 0.5 seconds, half a second. It's traveling in water. What is the speed of the wave? What's the wave speed? All right, well, You see the wavelength is given to you directly, but frequency is not given to you. It says the time between the crests. That's the time it takes one wave. That's what between the crests mean. If you go from crest to the next crest and it takes half a second, that's a half a second per wave, per cycle, per one of these, okay? That means it happens every half a second. Well, that's the period. That's how we define period. That's capital T. Well, period is the inverse of frequency. So the reciprocal of 0.5, 1 over 0.5, is 2. So if we know that that's 2 hertz, 2 per second, we can take the formula of wave speed equals frequency times wavelength. We're given the wavelength. We're given the period. We use the period to calculate the frequency by taking 1 divided by the period, 1 over 0.5 seconds equals 2 hertz, 2 per second. And now we have the wavelength and the frequency. We multiply them together, and we get 20 meters per second. Seems like a little bit of work. You had to turn the period into frequency and then use the frequency times wavelength to get your answer. Now, remember, period is a unit of time. Wavelength is a unit of length. Velocity is just length divided by time. So you could have just skipped all that, and we didn't talk about this formula, but you could have just taken the wavelength and divided it by the period, because wavelength is meters, period is seconds, meters per second is a velocity, and just gotten it directly. You could have just taken 10 meters divided by 0.5 seconds and gotten the exact same answer, 20 meters per second. Whichever way you're more comfortable with, go with. The first way that we did is the way you might want to think about it in order to get frequency, but the second way is to get the answer quicker. All right, so now let's talk about the two major categories of waves: transverse waves and longitudinal waves. These are the two most common versions, and they differ. They both can travel forward or travel up or travel back. But if we're traveling in a direction, what's different about them is one of them has the wave motion, the vibration, moving perpendicular to the direction of the wave, and that is the transverse wave, B, the second one. The wave is moving up and down, but the motion of the particles are moving up and down, but the wave is actually traveling forward. Whereas in the longitudinal wave, the wave is moving forward and the particles are moving forward and backwards. So they're in the same line. They're along the same line, and that is longitudinal. That seems a little weird, and it's basically what you have are particles that kind of compress together and then spread out and compress together and spread out, and that motion of compressing and spreading is moving across the wave. So you'll see the compression, and the compression will be over here, and then compression and expanding will be over here. And we call that compression, compression is compression. That expanding is called rarefication, and we'll show that in a second here. So you have these two very different waveforms. So in the transverse wave, I have a slinky here, and let's see if I can make it do this. But if I do this with a slinky, if I expand it long enough, you might be able to see that the wave is moving up and down. And if I vibrate it fast, you can see the wave is making a transverse wave. The up and down motion is perpendicular to the direction of the actual wave. So that it's going up and down. I could have done it side to side. That would still be perpendicular to a forward direction of traveling. That's transverse. So the medium of a transverse wave, whatever the transverse wave is flowing in, and it might be flowing in nothing, like light. Light doesn't need anything to do that. But the actual motion will be perpendicular to the direction of the wave. It's either up and down or side to side as the wave is moving forward. And there are lots of examples of transverse waves. Vibrations of a musical string is probably the easiest to see. If you take a piece of string and hold it tight and you have a third person pluck the string, or if you have a guitar or some musical instrument with a string, you pluck it, the vibration will happen. Usually you only see half a wavelength because it'll be up and then it'll be down. That's half a wavelength. But that's a longitudinal wave. It's moving along the wave, but the motion is up and down relative to the length of the wave, the length that the wave is moving across. Light waves all do this. In fact, if you have a light wave going in this direction, you might have an electrical wave in the light wave. The light wave is actually the electromagnetic wave is called electromagnetic wave. All light is part of the electromagnetic spectrum. It's called electromagnetic because it actually has two waves: an electric wave that's going like this, and a magnetic wave that's going perpendicular to it. But both of these are perpendicular to each other, and they're both perpendicular to the direction of the wave. And we'll talk about that more when we talk about light waves in another unit. But both waves in the EM waves are perpendicular to the direction of the wave. And these include all the EM waves: radio waves, microwaves, infrared, visible light that we can see, ultraviolet waves, X-rays, and gamma rays. Another example of a transverse wave are what we call the S waves from earthquakes. Earthquakes form a couple different kinds of waves, and the S waves are transverse waves. The motion of the solid rock that it goes through is actually an up and down motion as the wave is traveling through it, and they provide a certain amount of geological information. All right, so the distance, we're going to do a little quiz on some of the terms here. The distance between adjacent peaks, remember these are adjacent crests, that's what we call the peaks, in the direction of the travel for a transverse wave is called the frequency, period, wavelength, or amplitude. So this is a length, it's a distance, that's your clue, and it is in fact the wavelength. The wavelength is a length between adjacent peak to peak, which we call crest to crest, or adjacent trough to trough, or any repeating unit shown here in the bottom wavelength version. So the wavelength, lambda, is one full repeating unit of the wave. And for a transverse wave, it's easy to measure it from peak to peak, from crest to crest, or from trough to trough. Either one would work. The vibrations along a transverse wave, so this is the movement that it vibrates as it's traveling, move along the wave, perpendicular to the wave, both or neither. Well, transverse waves, they're always perpendicular. So if the wave is moving this way, if the wave motion is moving this way, its vibration is up and down or side to side. Anything that's perpendicular to that line. It could be at an angle too, as long as it's perpendicular to the traveling motion. So here's a transverse wave. The motion up and down is perpendicular to the motion of the wave traveling itself across the wave. Longitudinal waves are very different. These are medium waves. This is where the medium, whatever it's traveling through, vibrates parallel to the to the direction of the wave, to the direction of the energy transfer. And what that means is motion in and out is along the length of the wave. And I'll try to do this with a slinky. I don't know if you'll be able to see this. I'll do it upright because the slinky that will flop like this if I do it otherwise. But if you can see, I'm doing it this way. I don't know if you can see the little compressions in the spring at different times. It's probably easier if I expand my screen like this. And now you can see it's compressing up. There's a little bit of transverse motion because I can't keep it straight. If you want to see what most people do, they just take this thing, and if I just go like this, you'll see the part where the spring tightens, actually pinches between itself. You get little bunching of the spring like this. That movement is the crest of a longitudinal wave. So you'll have that motion of the thick part of the spring where it compresses together and then expands. So the part where it's stretched out, that's the rarefication. The part where it's pinched together like that, that's the compression of a longitudinal wave. I know that's can be a little confusing. Okay, so whatever medium the longitudinal wave is traveling through, it's going to vibrate parallel, in and out, in and out, in and out, to the direction of the wave propagating to the direction of the energy that's actually being transferred by the wave. So this back and forth motion consists of these compressions, that's the waves, the medium in the wave squeezing together, and then rarefactions, which is the stretching out of those regions that were compressed. So sound waves are the most classic example of a longitudinal wave, and this could be a sound wave through any matter, solid, liquid, gases, even plasma. As sound leaves our mouths, there are pressure waves that are being formed in the air, and the air is microscopically squeezing together and then spreading out and squeezing together and spreading out as the wave propagates through the air. It's compressing and rarefying, as the wave travels. But the air itself is only doing a little bit of vibration and moving. The wave is what is traveling. Okay. So longitudinal wave, here's a depiction of a longitudinal wave. And you can see the compression of the molecules of air. If you had a tuning fork and it rang, it would have this wave form, but the wave is not this up and down. It's this compression and rarefaction, compression, rarefaction, compression, rarefaction. So you get these high pressure, low pressure regions of air that are spaced as the wave is passing the air. This is the sound wave itself. And you see this with sound waves in any kind of matter. You also see this with another kind of earthquake wave called the P wave. These are pressure waves that actually travel through solid rock that move as longitudinal waves. So the rock is actually compressed and expanded, on a microscopic level, so it's not huge amounts. But these can travel, and they can travel long distances and even go through the Earth's core to the other side of the Earth. So this is why people can measure earthquakes sometimes from great distances across the Earth. All right. So the wavelength, lambda, that's the symbol for wavelength, of a longitudinal wave is the distance between, now remember, with a transverse wave, it's the distance between crest to crest or trough to trough. For a longitudinal wave, it's the distance between A, successive compressions, successive rarefactions, both or neither. Well, it's both. If you have these compressions, those are your crests, and the rarefactions are your troughs. The most rarefied, the thinnest part of the rarefaction, that is the trough. The densest part of your compression, that is your crest. So you can measure it on the left here between two different compressions, right between the center of the two compressions, or on the right between the center of two rarefactions. Either one will give you the same wavelength, as long as they're adjacent rarefactions or adjacent compressions. All right. So let's talk about wave interference. Now, this is what happens when you have more than one wave interacting with another wave, okay? And you can have two waves, you can have dozens of waves, you can have any combination, but we're going to keep it to two and keep it fairly simple. So whenever two waves interact, right, they're crossing each other, at any one point in time, those waves will just mathematically add to one another. And sometimes the wave is high, it's a crest, and sometimes the wave is low, it's a trough. And think of the crests as positive numbers and think of the troughs as negative numbers. And the middle would be zero. The middle line of any wave is zero. And you just mathematically add these together. And this principle of adding these waves together to get the composite wave, the total wave of the two, is called superposition. You're positioning one right on top of the other and adding them up to get the new wave that results from the combination of the daughter waves. All right. So these waveforms are just mathematically added, and you'll get new shapes and new patterns, and you're actually going to do this in your problem set. So there are two major categories of interference, but in reality, you get much more complicated mixes of these two. One is called constructive interference, and one is called destructive interference. And constructive interference, let's say you have two waves, and let's say the waves look exactly the same. They have the same frequency, they have the same wavelength, they have the same amplitude. They're going up and down just as high as each other. Well, if those two waves happen together and they meet each other, they just add together. The troughs will add to the trough, so you get a deeper trough, and the crests will add to the crests, and you'll get a higher crest. And the middle part, what we call the node, where it hits the 0 point, and in each of these waves, there are three nodes, one in the beginning, one in the end, and one dead center in the middle. Nodes are where nothing happens. It's zero amplitude for that part of the wave. But if you add these together, you'll get this reinforcement. So if you were to add the two crests in dark blue and the two troughs in light blue, you'll end up with this new waveform that combines the two. And this is a situation where we call the waves in phase with each other. They're lined up exactly with each other, and they'll reinforce each other, and you get constructive interference. In other words, the two they come together to make something greater than what they were by themselves. But you also have destructive interference. Let's say you have two waves that what we call are completely out of phase. When one is up, the other is down. When one is down, the other is up. And if you line these up and mathematically add the positive numbers of one with the negative numbers of the other, and the negative numbers of one with the positive numbers of the other, you're going to end up with something that looks totally flat if they're exactly the same waveforms but reversed. And you can get reversed waveforms by just shifting it a half a wavelength. It's shifted out of phase by half a wavelength. And so they'll end up canceling each other out. Now, oddly enough, this is exactly the technology that's used in noise canceling devices like noise canceling headphones. With noise canceling headphones or other noise canceling devices, there is some microphone that's picking up the ambient sound, the sound all around. It's analyzing the waves, it's plotting out the waves, and as quickly as possible by this technology, it's creating a new wave that is exactly opposite in shape. So anything that was up is down by the same amount, anything that's down is up in the new wave, and it beams out this new wave on top of the sound that's already there. And what happens is you have the sound that's there and this new anti-sound that's created by a new speaker with your device, with your canceling headphones, and the two together form a flat line. The whole thing becomes zero, and that's how noise canceling works. You're creating another wave quickly to match the other wave, but in the opposite direction, the opposite amplitudes, and therefore you end up with a zero wave as a result, zero amplitude wave. Well, you can see wave interference yourself. You could actually do this yourself. On the left here is a sophisticated diagram from two sound sources or two light sources of waves, but the right drawing here, actually it's a photo, is just water. And if you take two pebbles and you gently drop two pebbles about the same size from the same height into water, they'll both form rings of waves that ripple away from the pebbles where the pebbles hit the water. Well, it turns out when those waves hit each other, if a crest hits a crest, it'll make a higher crest. If a trough hits a trough, it'll make a deeper trough. If something else happens, it'll be somewhere in the middle. And you end up with these beautiful interference patterns. And you can actually look at this and you can see these rays coming off that represent either deeper parts of the wave, deeper troughs, or higher crests as a result. And there are a lot of it you can see is somewhere in between. And you'll notice they're almost repeating patterns of where the interference is constructive and where it's destructive in this. So at points in the region where the waves arrive out of step, again, we call that out of phase. The waves aren't matched with crest to crest and trough to trough. That's out of phase. So standing waves are an interesting phenomenon. In a standing wave, this is what happens when one side of the wave is stopped dead. So an example here is if you have a rope tied to a wall or doorknob or something that's not going to move up and down, and then you whip a wave into that rope or whatever it is you're using. Well, it turns out that when you do that, you set up what's called the incident wave, the wave you created. It's the one that goes in and comes and hits the wall and then is reflected back from the wall. When it's reflected back, it'll go back, and sometimes those waves, the wave coming back will be shaped the same way as the wave coming in, and that would be in phase. If it was to come back in the opposite direction, where the down part of the wave that you sent matches the up part of the wave that's coming back, they would cancel, and you'd end up with a flat part of the wave. And but if you do it and they reinforce each other, so the incident wave is the same general shape as the reflected wave, you can get these various patterns. And if you whip it fast enough, you could see the waves. You'll get one that looks like this, where you have a trough over here and a crest over here, and then you get another one at the right after that where it's just the opposite. So one's like this and the other is like this, and you end up with this bottom diagram of this girl that has these flapping waves that look like the wave is moving very fast, and the center, what do we call the nodes? The nodes are the part that don't move. That would be the ends and the middle of this particular wave that you'll notice is only one wavelength long. It has only one repeating unit. It goes up and it comes down. It goes up, down, and then back up to the original position, the same height as where the girl is holding the rope. that would be one full wavelength. So in one full wavelength, you have 3 nodes, one on one end, one on the other end, and one in the middle that didn't move up and down. And when you flip it fast enough with the right frequency, you can get this going. I don't know if I can do this. I'm going to try to do it with this slinky. I might be unsuccessful, but I'll do my best here. So I'm going to open this up, and if I can get this just right, it's kind of hard to see. There it is. There it is, right there. You can see a standing wave. That's where you've got the middle part is barely moving, and the sides are flipping up and down on the other side, but the center is more or less constant. That would be the center node in there. But you can do this for yourself if you want. So that would be a standing wave in a wave form, but you really need a stationary end, a rigid connection at the end. So the nodes, as I mentioned, are the parts that have minimal energy or zero energy. They're the parts that aren't vibrating, essentially. They stay the same and everything's vibrating around them. It just happens that that part is the center of the wavelength, and therefore it doesn't really move up and down. So antinodes are the opposite. Those are the ones that move the most. So antinodes are the parts of the rope or the string or the slinky that go up the most and come down the most. Antinodes have the most vibrational movement in place. That's maximal energy, whereas the nodes, they're essentially not moving at all. They're just right there. They might do a little movement, but they're almost no energy in that place. So antinodes and nodes will be actually evenly spaced no matter how many waves you have in the thing. If you shake it really fast and you get lots of waves, or you shake it slowly and you just get half a wavelength, so it's a big dip and then a big loop up, and it's going back and forth. In any case, you'll always find evenly spaced node, antinode, node, antinode, node, antinode. They're all half a wavelength away from each other. A quarter of a wavelength away from each other, one after the other, after the other, after the other. So you can do this yourself by tying a tube or a thick rope or a slinky or whatever to one end, or have somebody hold one end and then you whip it back and forth. So if you were able to do this with, say, a rope, and you got half a wavelength, you would have 2 nodes, one on either end, and the middle that moves the most up and down, that's the antinode, the thing that has the most movement. Node is no movement, right? In the second case, you shake it a little bit faster with the right frequency, and now you'll get one full wavelength form. Well, you still have a node on the end and a node on the end, but now you have a node in the middle, and that's one full wavelength, but you also have 2 antinodes. One part that's 1/4 of the way through and one part that's 3/4 of the way through that goes up and down, and the other one goes down and up in reverse. And then in example C, you're moving it even faster, and now you get 1.5 wavelengths from one end to the other. So the ends are still nodes because they're not moving that much, but you have 2 more nodes in the middle, and the whole thing represents 1.5 wavelengths, which means there are 3 antinodes, 3 parts that really are whipping up and down. So the first one's up and then down, the second one's down and then up, and the third one's up and then down in this last example here, C. And standing waves happen a lot in music, in guitars. When you pluck a string, especially the shorter the string, the higher the frequency because it'll vibrate faster, and that is perceived by human ears as pitch. Pitch is not an actual quantitated thing. It is something that is related to our perception of frequency. We give pitch letters like A, B, C, D, E, F, G for musical notes, or if you're in other parts of the world, they use do, re, mi, fa, sol, la, ti. But those are the pitches related to frequencies, which is the actual quantitated measurement of that frequency for the string. And this can happen with strings, but it also happens with other things that vibrate in musical instruments. In trumpets and wind instruments and other brass instruments besides trumpet, it's the air that's vibrating inside the tubes of the musical instrument, and they set up waves. So those are forming waves, sound waves inside the air in there. The strings are forming waves along the length of the string. In drums, you have waves on the membranes of the drum. So you hit it and a wave is spreading out from the place that the drum head is hit. So all of these are examples of waves, and if you hit it and you get that ring, you can get standing waves in these instruments because they'll continue to vibrate and eventually dampen down and the sound will stop. All right, so Doppler effect is an interesting effect that happens with any kind of wave, and it's especially important with both sound and light waves. We'll talk about sound first, and you probably already experienced Doppler effect with sound waves. If you hear a fire engine or an ambulance approaching you, you'll hear it go up in pitch. It's going up in pitch because it's going up higher in frequency that you perceive. Now, is the real frequency on that fire engine or that alarm changing? No, but it's approaching you fast. So what happens is, instead of the waves hitting, if that was stationary, the waves would hit you at whatever speed the waves would hit you. But if it's moving towards you, the waves are hitting you faster than you expect, faster than they normally would get to you. And as a result, you perceive them as a higher frequency and your ears perceive them as a higher pitch. So what you hear is, as the fire engine or the race car or the siren is approaching you, you'll hear the frequency go up, the pitch go up, it'll go as it's coming by you, and then as it goes away, the waves are taking longer to reach you from the source of the sound on the truck, and therefore they'll be spread out, and you won't hear, the waves will hit you less frequently, the wavelengths will be longer to you, you feel like they're longer between them, and the frequency is longer, and therefore the frequency will come to you less frequent, and therefore it'll sound like a lower pitch to you. And that's why when a race car goes by you, you'll hear that going up in pitch and then coming down in pitch. It's like, and it goes down. That is the Doppler effect coming as approaches you, getting higher in frequency, and then the Doppler effect of the frequency going down as the object is going away from you. And the same thing happens not only with sound, but also with light. And light, you can't really detect it very easily with your eyes. Sometimes you can actually, but you have to have really big changes in speed of the source of light in order to see changes in the perceived frequency and wavelengths of light. And in fact, this is what people have done since the days of Hubble by noticing that stars and galaxies spin. So one part of the star approaches you and one part of the star is going away from you as the star is spinning very fast. And as a result, if you look at the color of light on one side, you'll see the color of light get lower frequencies as it's going away from you and higher frequencies as it's coming on the side that's coming towards you as it's spinning. So one side will look higher frequencies like blue light and the other will look like lower frequencies like red light. And you can actually analyze star speed of spinning by these differences in the wavelengths that come from one side of the star versus the other side of the star. Now, this is not easy to do, but it is done. A more useful, an easier use of this is to look at whole stars or whole galaxies and look at how much the light is changed that should be coming from it, and instead you see different wavelengths and different frequencies coming at you because they're moving very fast towards you or very fast away from you. So we refer to this as the blue shift and the red shift when we're talking about light. So if light is moving towards you, if sources of light, if stars or galaxies are moving towards our galaxy very, very fast, and I mean very fast relative to the speed of light, which is incredibly fast, okay? In that case, wavelengths of light that we know should be reaching us are shifted, and we end up seeing different wavelengths of light that have higher frequencies than they should have had. And that tells us, hey, the only reason why these frequencies are higher is because this galaxy is coming at us super, super fast. And this actually happens with galaxies that are near our galaxy. Our galaxy is the Milky Way. So galaxies near our galaxy, like the Andromeda Galaxy and the small and large Magellanic Clouds, those are galaxies near us, and we're all coming up in closer together over time. And we can see this blue shift of the wavelengths of light they should have. It's shifted more towards the blue. Blue means, if you look in the visible spectrum, blue is the highest frequencies and red are the lowest frequencies. So when things are getting high frequency, we call it blue shift. When it's getting lower frequencies, we call it redshift. So redshift is when the objects are moving away from us. And most of the galaxies in the sky, not the ones near us, but most of the other galaxies are all moving away from us at unbelievable speeds, close to the speed of light. And because of that, wavelengths of light that we fully expect to come from those stars are redshifted. They're shifted to lower frequencies, more towards the red wavelengths. So wavelengths that should have been in the middle of our visible wavelength region, like green colors in the middle, they end up looking more red instead of green. And that's why distant galaxies tend to be red, and in the infrared, they're shifted so far that they're not even in the visible light range. And if you've heard about the James Webb Telescope, that is looking at infrared wavelengths of light. And this is good for the galaxies that are the furthest from us, that are moving the fastest away from us, because their wavelengths have been shifted so far in the red, many of them are invisible to us. They're now in the infrared wavelengths, even lower frequencies would put them in the higher wavelengths of the infrared. So wavelengths goes up, the frequency goes down, and they appear redder and redder until they're in the infrared and invisible to regular light. And the James Webb Telescope is specifically designed to detect infrared galaxies and stars, and as a result, we can see the ones that are moving super fast away from us, that are also incredibly distant from us, and we're now able to see galaxies that are so far away from us, we know that they formed close to the beginning of the universe. The universe is about 13.8 billion years old, and these galaxies apparently are already at a distance of 13.4 billion light years away. So very far away. Soon, they were formed very early after the beginning of the universe happened. So stars in very distant galaxies are moving incredibly fast away from us and will appear redder to us. They'll appear even in the infrared outside of the visible range. Rapidly spinning stars will appear redshifted on the side spinning away from us, and blue shifted on the side spinning towards us. So the Doppler effect occurs for sound, light, both, or neither. Well, we've been talking about both. It's both. Any waveform will have this. If an object is a sound source or wave source of any kind, light, sound, whatever, if it's moving towards you, you're going to get them hitting you faster. So the frequency will appear faster to you, and you'll feel like it's a higher frequency and a lower wavelength. So any type of wave, whether it's longitudinal, whether it's transverse, whether it's electromagnetic, whether it's sound waves, any wave, if it's the source of that wave is coming towards you, it'll have a higher frequency. If it's moving away from you, it'll have a lower frequency. Higher frequency is blue shifted, lower frequency is red shifted if we're talking about light. When we're talking about sound, we don't use the red and the blue. All right, so sources moving towards us, the waveforms reach us quicker. That's it. So we think the frequency is higher. And astronomers use the Doppler effect for light very, very well to measure velocities of stars, velocity of galaxies, spin rates of individual stars. It's really quite an amazing tool, and it's actually been used to help determine the age of the universe. Bow waves. All right, so I'm sorry, bow waves. They're actually pronounced bow waves. I keep saying bow. Bow waves, as in the bow of a ship. So bow waves form when an object that's producing waves, either sound or light, is moving as fast as the waves are traveling. So the source of the wave is moving as fast as the waves do. Now, this is an example right here of a bug sitting in water. It's not moving at all, and the waves that it makes are concentric rings that are spreading out. So that widest ring would be the first one it makes. Then the second one it makes is in the middle, is a little closer in. The third one it makes. So each wave towards the center is a newer wave. These are the old waves that have spread out far. But if this bug starts moving in a direction, the waves will start bunching up together, because each time it produces a new wave, it has moved its source of the wave. But if it moves as fast as the waves move, in this case the water waves, so the bug is able to move that fast enough, its new waves and its old waves will have the same right edge. They'll be moving at the same speed. So the old wave will be moving out, spreading out at the same rate that the bug is moving creating new waves, and therefore they will produce one wall of waves, and that's called a wave barrier, and we also call it a bow wave. So it's like the bow of a ship. If a boat is moving as fast as the water waves, it'll produce these bow waves. So supersonic jets that can or planes that can fly as fast as the speed of sound or faster, they will create bow waves. The record speed for a jet was from the X-15. X-15 is actually hanging from the ceiling at the National Air and Space Museum, and part of the Smithsonian Institute in Washington, D.C., and it went Mach 6.72. That means 6.72 times faster than the speed of sound, which works out to about 4,500 miles per hour. Incredibly fast. So this is the world record for a jet. Now, spacecraft have gone much, much faster than that. Once they're up in space, they can go considerably faster, but for a plane with jet engines, this is the fastest. And they will produce bow waves because they are moving not just the speed of sound, but even faster than the speed of sound. And these bow waves, if you look in diagram A, this is when the object's moving, when the sound source is moving, and B is when it's moving just at the speed of sound. So all the waves are bunched up in one place, and they're all spreading together on the right side of it. But once the plane moves faster than the speed of sound, now the new waves are actually ahead of the previous waves, and you still get a wall forming, a barrier wave, but now it's a full bow wave that's V-shaped. And the faster they move, the tighter the V gets. So if you look at D, the V starts off very wide in C, and by the time it gets to D, when it's moving even faster, it'll tighten up. And eventually it'll tighten up very tight if it's going much, much faster than the speed of sound. So this is the V is essentially produced by the leading wall of all the waves of sound that are being produced by the object. And the object doesn't actually need to make sound. It's going to be vibrating the air if it's flying through the air anyway. So you end up with what's called a shock wave. And the shock wave is the result of a double bow wave. It's the wave in the front of the plane, if it's moving faster than the speed of sound, where there's high pressure. The plane is pushing into the air faster than the air can essentially get out of the way. It's super high pressure in the front. And then on the back of the plane, it's moving away from the air and leaving a low pressure zone behind it. And because this all happens in 3 dimensions away from the plane, you end up forming this cone of shock wave. You get a high pressure wave in the front forming the bigger cone, and then a smaller cone just inside of it of low pressure falling immediately behind. And if you just look at a cross section of that cone, you have that leading edge of the plane, it's very high pressure, and the tail end of the plane is where it's low pressure. So if you were to measure the pressure with that little red gauge that's in the bottom of this diagram, you see the pressure is constant, and then all of a sudden it pops up at the tip of the plane, at the bow of the plane, and then it goes down at the tail of the plane, and then it comes back to normal again. So what happens is that wave is passing across the ground, or whoever's nearby, they experience the high pressure wave first hitting them, and then the low pressure wave immediately after, within less than it's a tiny fraction of a second. And as a result, this combination of a high pressure cone followed by a low pressure cone, it creates the sonic boom that you hear when jet planes are flying by faster than the speed of sound. And it doesn't even require the plane to be making noise. It's the plane moving through the air creating these sound waves. And you end up with a sonic boom as it's passing over the ground and people are listening. So in this case, the plane has already passed A, B, and C people, but the wave is following behind because the wave is not as fast as the plane is. So the wave will hit person B, and then eventually it'll hit person A, even though the plane has already gone past person A. And it sounds like a crack. You probably heard it if you've been near Dover Air Force Base, especially during the shows from the Blue Angels and some of the other jet teams. So it's the intensity due to the overpressure of the air, immediately followed by the underpressure of the air. It's the two cones traveling by you, and they create that snap in the air, that shock wave in the air. Now, the fact is, people have observed this long before planes were even invented. You can generate this with a bullet that goes faster than the speed of sound. It will create that crack as well if you're standing in the right position to hear it. And the crack of a circus whip, the tip of a circus whip, when you whip it and go, that tip is flipping around faster than the speed of sound, and it will create that high pressure, low pressure bounce of air and will create a mini shock wave. And that's why we hear that crack of the whip. That is a sonic boom, a mini sonic boom. And with that, we'll stop here.